move on to the another concept. I told you that there are two kinds of inductances. One is mutual, another one is the self-inductance. So now we have to study what is a self-inductance, and we should know how to find EMF generated in a self-inducting coil. Also, we should know the formula for self-inductance. That is, it is represented as a letter L. Let's see that. This next concept is that is called self-inductance. So then, what is the main difference between mutual inductance and the self-inductance? That is we need to understand. So while discussing the concept of mutual inductance, we took two coils and we have placed one coil along the axis, and we have derived and we calculated the equation. Sorry, we have derived the equation for mutual inductance, and also we saw the equation for EMF. But when we come to the self-inductance, we have only one coil. So then, whether one coil itself produces an EMF? Yes. So what happens is, in the self-inductance, what happens in the self-inductance is, whenever the current flowing through this coil changes with the time, if there is a rate of change of current, there is an increase or decrease in the current, then there is an EMF induced in the coil due to the current flow through itself, and this is known as a mutual inductance. Okay? And EMF is induced in the coil due to the changing current through it. So, and that induced EMF through the same coil, it is known as a self-inductance. Now, let us write a general formula to calculate that is a self-inductance. And we already know the formula for inductances, that is N into phi b, which is equal to K times I every time. That gives a relation between the magnetic flux and current. I mean, as a flux increases, current in the coil will also increase. So here we have taken only one coil, and we will change the current. The current will change continuously. As soon as the current changes, it will induce us a magnetic field. So because of it, as soon as the current changes, there will be change in magnetic field that will be linked with the same coil, so that it will induce an EMF, and that is known as a self-inductance. So magnetic flux linked with coil is, alright, that is N into phi b is equal to magnetic flux linked with this coil due to the changing magnetic flux due to itself and the current flowing through that, then induced EMF is known as self-inductance N into phi b, which is equal to, here I am writing as L into I. So in the case of mutual inductance, I have written M. So here I am writing L. L is called as, it is a constant of proportionality. Actually, this equation like this, N into phi b is a proportional die. If you remove the proportionality constant, then you will get a L. L means it is called as a proportionality constant, which is also called as a self-indulgence. So L5 is equal to L into. Then I told you that whenever the current flowing through this coil varies, it changes, it produces a change in magnetic field, because moving charges will produce a magnetic field. We know it already. So that is why this changing magnetic flux linked with the same coil, so that it will induce an EMF in the same coil. Okay. Now, how does this work? That is what we have to see. So let me to explain this. Let me take a diagram like this. Okay. So here we have a connector. So I am showing you here a simple diagram. So let me tell you the parts here. This is a battery, and this is called as a key, battery, key. This is a resistor. I mean, it is a variable resistor, and this is a solenoid, and this is the bulb. Okay. So when the key is pressed, when you press the key, then what happens is current will flow like this. Current will flow like this, and you have to set some value of resistance here, and I will explain why. To limit the value of current, that's only we have to set up the resistor thing. We have to vary the value of resistance of the lid. And the key means it acts as a switch. If you press the key, connection will be closed, and if you open the key, if you are not pressed the key, if you release the key, then circuit will be open. Yeah. Now, as you press the key, the current will flow through this solenoid, and the bulb will also glow. And as soon as the current going through this coil, there is a EMF will be induced, because once you press the key, the current will rise. The current will goes on increase. It will accelerate up to a certain time. After that, current flowing through the wire becomes a constant. So at the point of contact, I mean when you press the key, at that point of contact, suddenly the current will rise, will increase. So at that point of time, there is an EMF induced in it. And whatever the EMF induced, whatever the voltage induced there, that will oppose this current. It will oppose, and that EMF will in a direction, in an opposite to the direction of this current. What I am writing here, it is E. E is an induced EMF. Induced EMF opposes that current. That is why that induced EMF in this direction. How did you say? How can we say the E will be in opposite direction to that? From the Faraday's law, he said that whatever the induced EMF will tend to produce a current which opposes the magnetic flux that produced it. It is also told by Lenz. Lenz has also said that. Okay, so that is Lenz said that it is about the polarity of the induced EMF. That the induced EMF always opposes the cause for it. Which is a cause? The increasing current is a cause. Cause for what? Cause for the magnetic this one EMF. So that is why EMF in this direction and the current flowing in that direction, which opposing the increase in the current. So that should be there. Yes. So that is why EMF. That is why EMF in the direction opposite to the current direction of current. That is why this EMF is called as a back EMF. Because it will in a direction opposite to the direction of that current. That EMF is opposite to the direction of the current, and in the presence of this back EMF, in this EMF, we need some work to move a charge from one point to another, because it will oppose. It will oppose to flow current to that coil. That is why we need to do some work. So that is why the self-actor self-inductance will act like a electric inertia. So we all learned about inertia because of the mass. So we can give an analogy that L can be an analogy of a mass in mechanics. So you will learn about it. So why I said the electric inertia means you cannot easily pass the current. Why? Because there is a EMF developed in that coil. So you have to do some work. So there is some inertia. Okay. So that is why this self-inductance which plays a role of inertia. Okay. Now here I think now we got this point. So whenever you press the key, current will flow, so that the EMF induced will oppose the increasing current. For example, if you release the key, what will happen is the current will decrease in this direction. So as to oppose this decrease in current, the EMF will be along the direction of the current itself. I am repeating once again. When we release the key, we have already pressed it now. Once we release the key, current will decrease along this direction. To oppose this, it is decreasing in that direction. That is why EMF will be in the same direction of the direction of current to opposing that decreasing current. Okay, this will happen here. Okay, then one miracle will going to happen here, that is when you release the key, the bulb should not glow there because there is no current. But for a time being, it will glow very brightly. You can see a bright glow in the bulb because EMF, voltage or potential developed in this coil, which will give some current to glow the bulb. That happens when you release it. So this is what the concept of this self-inductance. So that is what I told you. Whatever the back EMF induced here, it can be called as a back EMF. So let's continue. So magnetic flux into the coil is compared N5 into L into I. So similarly, magnetic flux with the coil is also given by formula of magnetic flux for a n number of turns. This has a n number of turns. So n into phi b is equal to b into a. B into a theta is equal to take it as 0. It will be 0 there. B into a, no need to worry about it. B is, what is the formula for B? Due to a solenoid, that is V naught into N into I, current flowing through that itself times the area. V naught into N into I, and here you have written for a n number of turns, that is why we should write N into L, V naught, N into I times B into A, that is a N into B into 1 is 6. So this is another equation. So let us write this equation number 1, this is equation number 2. Equating, you have to equating 1 and 2. Let us equate these two equations. Once you equate this, L is equal to, you can write N into L into V naught and IA, so IA cancels out. That is why equating, you can write L is equal to V naught N square L into mu naught n square Am. So this is the equation for mutual inductance of the coil. So equation is L is equal to mu naught into n square into A. Yes. Now, can we write the equation for EMF induced in this one? I told you that the EMF, whatever the EMF induced is called as a back EMF. Then induced EMF. Whatever the induced EMF in the coil can be written with the help of this. From the Faraday's law, what we can write is E is equal to minus d phi b divided by d. And we know the equation for n into d phi b. Here it is n into d phi b. N into d phi b, which is equal to L into I. So minus L into di by. Because L is a constant here, it is a proportionality constant. I told it already. So that is why we have to take L outside and we left with the derivation of rate of change of I. That is why E is equal to minus into L into di by dt. This is the induced back EMF in that coil. So this is about self-inductance of this coil. Yes. Now look at this. Yes, let me explain in the case of mutual inductance also. If you look at this equation of mutual inductance, here it is a mu naught. Mu naught means it is a permeability of the free space. Okay, for a general case. While deriving any equations in a physics, we take permeability of the free space. For example, if you are introduced any other medium, see in the example of in the derivation of self-inductance, we have taken one coil, and in between the coil there was an air molecules. For example, if that coil, as an example, I am saying. As an example, if that placed in the water. So what is the medium then? Now it is a water instead of air. So that is why in that case we are not able to write the value of mu naught there. So there will be some other there is some alteration to this equation. How to alter this? See here, mu r is the relative permeability, then we can write this as mu by mu naught. So mu by mu naught means it is what is the relative permeability. It is the permeability of the any medium. It is a free space. Their ratio is called as the relative permeability. That is mu is equal to mu r into mu naught. So mu means it is the permeability of the any medium. Hence, you can take this note also. For any medium of permeability, that is mu r into mu naught. Then, in the case of mutual inductance, M is equal to mu naught N1 N2 pi R1 square mu naught N1 N2 pi R1 square into N. Yeah. So here you have to write this as mu. R you can write this also equal to mu means what? It is a mu R into mu naught N1 N2 pi R1 square. Okay. For any medium, magnetic moment will be like this. For any medium, the self-inductance L can be mu times N square A for any medium, which is equal to mu naught mu r n square E. So this is the another equation for self-inductance for any other medium if you have introduced in between the coil. So this is about concept of self-inductance and mutual inductance.